And here we go. We have liftoff. Propulsion continues to be nominal.
Our 68 chamber pressure looks good.
Rolling up. Roger, roll, Atlantic.
Water towers can fly! Yes!
Tango down to nominal.
Flight downside FD off. Bring in FD off. Off. It's orange!
45. Oh my god! Oh my god!
Decollage.
What is it?
Put that in the big bag, Eagle.
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
If the methane would be igniting in the flare, correct?
Yikes. You read? We don't need any more of these.
Hello, everyone, and welcome to NSF and the Intrepid Museum's virtual Astro live show, a live show that is supported through a NASA cooperative agreement awarded to the New York Space Grant Consortium. Today, we're going to be going into all things Europa as we talk about NASA's latest and greatest planetary science mission, Europa Clipper. We've got some amazing guests here who work on Europa Clipper that are here to discuss the mission, answer your questions, and more. First, though, let us all know that you can hear us and that everything looks good. Give us those 5x5s in chat. Everything cool. Everything looks to be going good. Awesome. Sweet. So my name is Hagen Warren. I'm a science editor here at NSF who will be your host for today's live show. Joining me is the amazing Summer Ash, who is an awesome science communicator and writer and a former rocket scientist and astrophysicist. Summer, how are you doing today?
And I'm so excited for this event, just like you said.
Awesome. We have some awesome guests here with us today. Do you want to introduce them for us?
Yes, I would love to. So today we are joined by Jenny Kampmeyer, who is a scientist systems engineer at NASA's Jet Propulsion Laboratory. And she works at the interface of scientists and engineers working on the Europa Clipper mission. And in a former life, she was a classical musician and orchestral librarian. So you better believe we're going to ask about that. Also joining us today is Dr. Sean Brooks, who is also at JPL on Europa Clipper, and he is the investigation scientist for the mission. And he previously worked on the Cassini mission to Saturn. So Jenny and Sean, I have two really important questions to begin with. One is, what's your favorite planet and why is it Jupiter?
I feel like most of us, though, everyone always says, what's your favorite planet? I think we're all obligated to say Earth because this is where we live. But if I had to pick a second favorite planet, it would definitely be Jupiter. But I'm interested to hear what Sean would say about that, given his background on Cassini as well.
No, I think you're exactly right about that. I mean, of course, we have to, respect our own mother planet. But yeah, it probably would be Jupiter. I'm partial to it. Was provided the material for my thesis when I graduated, got my PhD. So yeah, I'm a Jupiter person, definitely.
Nice.
Awesome.
What was that thesis on?
I wrote a thesis on Jupiter's rings. I think it was maybe only you could probably count on one hand the number of people who've written a thesis on Jupiter's rings.
That's awesome. So my second question that I'm hoping Kevin can help us with is, where is Clipper now? Like as of right now. So I'm hoping Kevin can bring up the eyes on the solar system.
Oh, yeah.
But I didn't know if you guys have like a telekinetic feeling for exactly where Clipper is.
Given that we launched less than a week ago, we are surprisingly far away from Earth already. And that's because we got this huge boost from our Falcon Heavy rocket. We're kind of on our way to Mars now. The first pit stop on our trajectory is at Mars to do a Mars gravity assist. And so, yeah, you can see kind of where our spacecraft is. This tool is really cool if you've never played with it. This Eyes on the Solar System, it is using real data from our spacecraft and from the Deep Space Network to track objects in the solar system, and you can see where Clipper is. And if you change the view to be kind of like a top down on the solar system, sometimes you can get a sense of just where it is. But it's something now. A couple days ago, it was like 5 times farther than the moon. So we must be even further now. So yeah, it's pretty wild.
Probably a fun URL to throw in the chat.
Mhm.
Well,
Yeah.
Yeah.
helps.
Yeah, and so launch was super exciting. I think there were so many people watching it. I was probably shaking with nerves watching it, but that doesn't even compare to what I'm sure you guys were feeling at launch. So walk us through launch day. What was it like? How did it feel knowing that something that you spent so much time on is launching to Jupiter? What did it feel like?
Sean, do you want to start?
Well, yeah, I think you're the one who's got the Um, it was exhilarating and it was nerve-wracking. I mean, at both. I mean, I think you can sort of imagine, thinking thoughts that I did not want to think, waiting for that thing to launch and just hoping that everything would go fine and watching it for as long as I could. I think I was unable to relax until I heard that the solar arrays that will be used to power the spacecraft had finally deployed. So it was thrilling. It was also great to be there with friends, with colleagues, and with my own family. I think getting to experience it with the whole Europa Clipper family was also fascinating. I braved a hurricane and a tornado as did Jenny just to see this thing, and spent an extra day in Florida just to give ourselves a chance to watch it. And I'm really very, very glad that I did.
Yeah, it was a totally surreal day, and it's still I feel like I'm still pinching myself a little bit that we actually launched and we're actually in space. I've seen a bunch of launches, but seeing something that you've worked on for years, sitting on top of a massive controlled explosion
Right.
to get up into space, and the fact that it goes from sitting on the ground where it's been for years and years to getting into the kind of like through the hardest part of the atmosphere and then into space within minutes is just it kind of blows your mind. I mean, space is only 50 miles away, right? It's closer than than the distance from Cocoa Beach, Cape Canaveral, where this is launching from, and Orlando, right? That it's a shorter distance than that, and extremely surreal and just absolutely amazing to see something that we've worked on actually go. It was a bit of a spicy count. We had like a little bit of a not an anomaly, but there was definitely some
They
telemetry
use the
that
word anomaly.
yeah, they used the word anomaly, but there was some telemetry that didn't look that was like a little bit out of family, and so they were doing some analysis of that and determined that we were okay to go. But that happened in the last 2 minutes of the count, so it was definitely exciting to a very exciting countdown. And then when it was going, it was like, okay, I guess we're actually going, and just yeah, very surreal. I've seen a lot of launches, but this one, of course, is just we'll never forget it. Incredible
It also
experience.
caught me a bit by surprise because at least at the viewing site where I was, there was no countdown. And then I blinked and all of a sudden it was taking off. And I wasn't really ready. And when they used the word anomaly, I thought there's no way they can resolve this in time to actually launch. And suddenly
That's right. Yeah. Yeah.
Jenny, you were also co-hosting on the NASA feed. How was that?
I was, yeah. So I was the co-host for the launch broadcast, which was, I mean, incredibly fun. It was so cool, getting to I got to interview the U.S. Poet Laureate. I got to, answer questions from the public and from kids, which is so satisfying. It honestly, in addition to it just being a ton of fun, it was a huge honor. I felt incredibly privileged to be able to represent, I mean, the literally thousands of people, over 4,000 people who've worked on this project over the years at different organizations, and to kind of get to sit there and be the face and help get people excited about this mission and show the humanity of the team was just an incredible privilege, and certainly an experience unlike anything I've had. And yeah, again, to not only get to do that, but on a project that I'm so passionate about, and representing a team that I care so much about. Yeah, it was a really special thing. It was really fun.
And you got
And
to step
exhausting.
outside and see it yourself. I was a little worried that you wouldn't be able to do that. So
I did the last couple minutes of the count, and then the first couple minutes of flight. There were two other commentators that took over that work for the launch services program, and so me and the other hosts were able to run outside and watch the launch and cry all the tears and try to stand upright, just a crazy experience. And then we ran back inside, got our headsets back on, our mics all mic'd up, and then okay, let's keep going with the broadcast.
Yeah. And while we're on the topic of, the way you feel about this mission and that you've worked on it for so long, how did you guys get involved with Europa Clipper? How long have you guys been working on this project? Because obviously you have to have been working on it for a long time for for this to be such an emotional experience. So walk us through, a bit of, how you got involved with Europa Clipper and, what exactly you've done with the mission.
Jenny,
Sean, do you want to start?
Oh, no, I can see the floor to you, Jenny.
Oh, okay, sure. Well, let's see. Compared to someone like our project scientist who's been trying to literally get this mission off the ground for about 25 years, I feel like my 5 years on the project is not that long. It is. I've been working on Europa Clipper for about 5 years, but I knew about the mission before that, and it was always a little bit of a dream, I guess, to get to work on this project because it just always captured my imagination, and so I've been kind of in this same role the whole time I've been on the project, where I kind of sit right on the boundary between the science team and our engineering team, and kind of help make sure that stuff isn't getting lost in translation between the two teams. Obviously, we all have the same goal of exploring Europa. Up until now, getting a spacecraft launch, we all had the same goal, but the coming from two different kind of disciplines, there's often things that kind of get lost in translation. So it's been a really cool job to be in that space. Before we mentioned this at the very top of the show, but before I worked on Clipper, I worked on a couple other missions at JPL, some Earth orbiters called SWAT and Sentinel-6. I worked on a CubeSat called Lunar Flashlight. And then before that, I had gone back to school as an adult for engineering. And before that, I was a classical musician. So I've had a bit of a non-traditional career path, but it's been an incredible ride now that I'm at JPL and getting to work on this amazing project.
What prompted that switch from musicianship to engineering?
Yeah, easy question, long story, of course, but I'd say the short answer is that I was I'd always had kind of a fascination with space and with technical things. When I did my music degree, kind of right after high school, I actually did start as an engineering major for about a year, and then I switched into music. And a lot of that was because I just got kind of intimidated out of the program. I didn't really feel like it was something I could do. There weren't a lot of women, and I just didn't really feel a home there. And it just felt like, it didn't feel right to me at the time. And so I switched to music, which felt more comfortable. And I absolutely loved my music career, like no regrets about that. But I think that interest in science was always there. And so a little bit later in life, I had, again, I'm making a long story very short, but one of the things that kind of kicked me down this path was that I happened to be in Florida visiting family and saw the last space shuttle launch, which I think was in 2011. And I had seen launches as a kid, but that one, for whatever reason, just really captured my attention in a way that others hadn't before. And I just literally that day was like, I think I need to go back to school and like change my career. And so I started kind of thinking about that. And then that ultimately led to me, like applying for schools and going back to school full time. So, I absolutely loved my music career and it was a lot of fun. And also this was a great decision to come do this instead.
Nice. And Sean, were you always interested in science and engineering?
Yeah, there was never really an aha moment for me. I have been fascinated with planetary science, not just astronomy, I mean astronomy too, but planetary science since I think about the age of 7 or 8. I remember checking out books at the school library back in 2nd grade. So yeah, it's been a lifelong love, and the fact that I can actually do something that I've had a direction for my entire life, and that I've had something that I've always been passionate about and wanted to do and actually get to do is really exciting to me. So Mondays to me are not a thing to forget. I look forward to getting back to work every day.
And so what is your work as part of the Clipper team?
So I would say, so I'm not the investigation scientist. I am an investigation scientist. The Europa Clipper mission has 9 instruments, 9 dedicated science instruments, and each one of those instruments has at least one investigation scientist, and we serve as representatives for the instrument teams which are distributed across the country, and project science back at JPL. So I'm sort of a go-between between the Europa UBS team and the Europa Clipper mission at JPL.
Got it. So what's an example of like a day in the life of you doing your job prior to launch?
Lots of meetings. Just sort of seems to be life at JPL. But and there was sort of a lot of thinking about requirements and making sure that the investigation that we have planned is going to do the science that we intend it to do. And planning forward, looking forward and thinking about the science we get to do. There winds up being lots of little details that you sort of, have to work out. For example, when we want to observe a star, which we will do several times, trying to figure out which stars we want to observe, which ones are close enough, working through little details like that.
Cool. And so while we're on the topic of, talking about the science and stuff like that, let's talk a little bit about the design of Europa Clipper and its instruments. Do you guys want to give a brief overview of, the instruments that Europa Clipper is taking all the way to Europa and,
Sure.
what type of science you guys are going to be really looking into whenever you're at the moon?
Yeah, absolutely. So yeah, as Sean said, we have this really incredible payload of scientific instruments. We have 9 individual scientific instruments, and then we also have a gravity and radio science experiment, which uses the telecom system, so it uses some of the antennas. And so we kind of sometimes call our payload like a really high-tech Swiss Army knife because each of these instruments has kind of a unique function, but they all complement each other, and they are, kind of going to help us understand globally what is going on at Europa. So you can kind of loosely categorize the instruments into two groups. We have a group of remote sensing instruments and a group of in situ instruments. And so remote sensing instruments are basically anything that is taking science from a distance. So kind of the easiest example to understand there is a camera, right? A camera kind of takes science from a distance. When you want to take a picture of something, you don't stick the camera right on the thing you want to take a photo of. You kind of step back and take a photo from a distance. And so we have a suite of instruments that are doing that kind of scientific exploration. And then the in situ instruments, that's a Latin phrase that basically just means like in place. These are things that are going to be kind of directly measuring the thing that they are studying. So we have a dust detector and a mass spectrometer that have sensors on the front of their instruments, and as little particles kind of fly past the spacecraft, they'll be able to kind of directly taste them or sniff them, figure out what they're made of. Another good example is our Europa Clipper magnetometer will be directly measuring the magnetic fields. We have a plasma investigation that will be measuring the plasma fields. And so that's kind of, just a broad overview of our scientific instruments. It's a really incredible suite, and each one is studying something that will help us understand things like the geology of Europa, the composition, what's it made of? What are those, funny looking red stripes all over the surface? Like what are the kind of constituent components of each of those, as well as trying to understand the interior structure of Europa. And so even though we're just doing flybys of Europa, we're not landing on the surface, we can figure out an incredible amount of information about the interior from studying things like the magnetic fields, the plasma fields, from looking at the gravity environment will tell us kind of about the structure. We also have an instrument that's an ice penetrating radar that will actually send radar signals into the moon and will help us understand things like the thickness of the ice, like how much ice is there? Are there spots where it's thinner? What does the structure of the ice look like? So those are kind of our main science goals: to understand the geology, the composition, and the interior. And then all of those science goals serve the larger question of, is Europa a habitable environment? Could it support life?
Yeah, and and while we're still here on the topic of instruments, I'm sort of wondering, what was maybe the hardest instrument to design or construct? Was there a particular instrument that seemed to, give you guys the most, I don't want to say issues, but was sort of the hardest one to work with, to design, to integrate, to test? Could issues with testing just be because we're not at Europa here on Earth? So yeah, just what instrument maybe gave you the most flack? We'll say that.
I have some thoughts there, but I'm curious what Sean thinks first.
Okay, I'll go first on this one. I mean, and it's problematic isn't the right word. It's just it's a very the reason experiment is a very complicated experiment. By its very nature, it needs to be electromagnetically isolated. And because of the nature of it, it sits on the solar panels, right? So the solar panels are a source of electromagnetic noise. And you obviously can't test it easily with the solar panels all deployed the way it's supposed to be. So that is a very complicated design. There are a lot of challenges in making sure that it will function as it's supposed to. And it will be deployed soon. It hasn't been deployed yet. So it, in some ways, was not able to be tested in the same ways that some of the other instruments were. It's going to be a fantastic investigation. I really can't wait to see the data that it returns. Of course, I'm going to have to wait for, another 6 years. But I think that Reason was one of the instruments that really posed a lot of challenges. The exciting data is sort of commensurate with the challenges in implementation, I think. I don't know if you would agree with that.
Yeah,
Jenny,
that reason is definitely one of the ones that popped in my head for sure, just because it's unusual. It's an instrument mounted on our solar panels. All of our other instruments are mounted on the body of the spacecraft somewhere, and this one, Reason, actually has, 6 antennas altogether in 2 different frequencies, and they all have to deploy. And this photo that you're seeing right now is kind of in the pre-deployment configuration. So the antennas all kind of folded up inside of that mechanism. And yeah, we were never able to test, some of the interactions of Reason with the rest of the spacecraft on the ground for a lot of reasons. Pun intended. And this other photo that you can see here too, the very upper left, it's kind of hard to even see Reason in this photo, but the very upper left, there's like a tiny little, skinny little antenna that you can see at the very top of that boom. That's one of the Reason antennas. And then the very long boom that's right next to that spiral staircase is one of the other antennas. And so we were able to do some testing of them. And this is a facility at JPL that is way up on a mountain, kind of away from the rest of the facilities, because the testing of this kind of instrument is really complex. So yeah, Reason definitely comes to mind to me as particularly challenging from a technical perspective. The other 2 that popped in my head were MISE, one of our spectroscopy instruments, and ICE, which is one of our cameras. And that's because both of those, it's maybe not obvious from looking at a photo of them, but MISE has an internal mirror that can move. And so while it's kind of fixed on the body of the spacecraft, that internal mirror can move to effectively point the instrument to different locations on the surface. And ICE, our camera, the narrow angle camera, also has a gimbal, so it can also point. It kind of looks like a long telescope that can point back and forth. And so those also pose unique challenges because they have not only a sensitive instrument, but a component that moves inside of the instrument. And so that adds additional technical challenge as well. So, I think though, if we went through every instrument that we have on board the spacecraft, we would find something to talk about that is technically challenging. These, not to overstate the point, but this is a really advanced set of scientific instrumentation. The mass spectrometer that we're flying is like one of the most advanced mass spectrometers that's ever flown in space. And so it came with its own set of technical challenges and testing challenges and things like that. Yeah, that's a picture of mass specs, our mass spectrometer. And it's definitely the most sci-fi looking of the instruments. And you can almost just see how complex it is just from looking at it, right? It's a very complex piece of machinery. So.
And so it's not just that they're complex for the sake of being complex, it's also the capabilities that these instruments have, which,
Yes.
The ultraviolet spectrograph, UVS, is just the 6th one in a line of ultraviolet spectrographs that were built and designed at Southwest Research in San Antonio. But as you know, it's also got, it's the most advanced. It's got the most sensitivity of all of them, and so that's sort of the story for a lot of these. They are sort of state of the art in many ways.
Yeah, exactly.
Will those
Cool.
instruments be tested and calibrated any time along the way to Jupiter, or not? Some of them, can some of them not be tested until you actually arrive?
Either one of us could probably take that. Yeah.
Yeah, I mean, the story is sort of different for every instrument. Certain instruments will be deployed and tested sooner than others. I think the first couple, and correct me if I'm wrong here, Jenny, I think the magnetometer and Reason will be some of the first instruments deployed and checked out. UBS will be checked out relatively early. Some of these instruments have protective covers that won't be released until later in cruise, and so they won't be tested until we're further away and closer to Jupiter. And I think some of them actually will need to wait until we get into the Jupiter system for a full set of calibrations to be implemented.
Yeah, Sean basically nailed it. Yeah, there's kind of it depends on the instrument. You know, some of them we need to deploy early. So for example, and I'm speaking now from an engineering perspective, but the Reason antennas that are on the solar arrays and the magnetometer, which is the large boom that is sticking off the top of the spacecraft. Well,
Tail.
top is relative, but you know, that kind of tail sometimes that we talk about. Those need to be deployed because we have designed the spacecraft to function in terms of like being able to control where it's pointing. We've designed the spacecraft to function with those things deployed, right? And so we want to deploy them soon because that's kind of how we plan to operate the spacecraft. And so the sooner we get things deployed into kind of their final configuration, the better it is from kind of an engineering perspective. And of course, there are scientific reasons too that you may want to check things out earlier. The other thing that might be interesting to mention is that I mentioned briefly that that now that we have launched, our spacecraft is on its way to Mars because we're doing a Mars gravity assist, and that actually provides a really interesting opportunity for calibration for a couple of our instruments. So e-Themis is our thermal imager, and the E in e-Themis is for Europa Themis. And there is another Themis instrument that is at Mars currently. And so being able to kind of turn that instrument on and take some data with the one that's on Europa Clipper while we're at Mars provides a really rare and kind of valuable calibration opportunity, because we've been operating a very similar version of this instrument at Mars for years. And so to be able to calibrate those two against each other is incredibly valuable. And the Reason instrument is also another that we'll be doing a calibration at Mars for kind of similar reasons. I keep using the word reason when talking about Reason. But kind of the same motivation there, that we understand Mars really well, and so being able to calibrate the Reason instrument once we get to Mars is incredibly valuable. So there are a couple calibrations, things like that we'll do early in cruise as well.
Nice. While we were having the spacecraft spin on screen, I was reminded, just for anybody watching who doesn't know, this spacecraft is large. Like that wingspan is over like a tennis court, right? And is the spacecraft bus kind of one of the larger buses for a mission?
It is. So this spacecraft is the largest planetary spacecraft that NASA has ever built, and so that's both in terms of size. It's absolutely massive. It's about the size of a basketball court, which to me doesn't sound like that big, because we're kind of used to like seeing basketball courts on TV, and it's like, oh, that's not that big, right? It's just a basketball court. That's the same size as the toe to the crown of the Statue of Liberty. So it's really big. It's really, really big. And that's what the solar panels deployed. And then it's also the heaviest spacecraft that NASA's ever sent for planetary exploration. It's about we have about 6,000 pounds of propellant on board, and that's about half the mass. So our spacecraft weighs about 12,000 pounds, which is just absolutely massive. It's a huge, huge spacecraft.
That's bonkers. And wasn't there a thing, Hayden can correct me if I'm wrong, but that the reason why the boosters weren't retrieved was because it was so heavy, and because the orbit that it had to reach, they had to stay on even longer than normal and put them out.
Correct.
Yes.
Yeah, exactly. We needed like every bit of performance out of the Falcon Heavy rocket as possible. And so I learned a couple things that I thought were kind of fun that I didn't know about beforehand, which is that, yeah, so it was the kind of fully expendable configuration of the Falcon Heavy, which means that the boosters don't come back to Earth and land like they have on other launches. Uh, so that's so we can use every drop of fuel to get us into this, really crazy orbit. That also means that they took off things like the landing gear and the fins and basically anything that they didn't need, that would support a landing. They took that off because, well, that's weight that you don't need to carry to space if you don't need it. So, okay, like strip off the excess hardware that's not needed, and then also the liquid oxygen that gets put into the rocket has to be super, super chilled, incredibly cold. I had never really thought about like why that is. I always kind of assumed like must just make the fuel more efficient or something for it to be really cold. And that maybe that is partially true. I'm not actually sure because I'm not a propulsion expert, but I do know that part of the reason for cooling it down is so that it gets denser, so that you can fit more of it in the tank, so that you can get more performance. So just by cooling it down, it makes it denser, and that way you can shove more of it in there to get more performance out of the rocket. So, which I didn't know that until like I just knew I always knew you had to chill liquid oxygen, but I didn't totally understand why, and I thought that was really neat.
Yay, physics.
Yeah.
Yes, yay physics. um, but and so part of the reason why Europa Clipper is such a big spacecraft is because of those solar arrays. Um, as we just talked about, they're huge, and that's because Jupiter is pretty far away. If my memory serves me correctly, it's about 5 AU, which is about 5 times the distance of an AU, an astronomical unit, is the distance between Earth and the Sun. And so multiply that by 5 and you're at Jupiter. And because of that, the sun is pretty far away. And so you need these huge solar arrays. And so I've got about 2 questions here. The first is, initially it seemed like, and this was before my time, I believe, but whenever we were really talking about, whenever teams were thinking about how are we going to power the spacecraft, were RTGs ever considered? And then, because we know Mars rovers like Curiosity and Perseverance use RTGs. And then why did you guys end up going with solar panels? And then we have a question from chat actually that's asking, are the Europa Clipper solar panels made using high efficiency germanium substrate instead of, the usual silicon base?
Sean, do you want to talk about the RTGs? I feel like, especially with your Cassini background, like might be interesting to hear.
Yeah, no, it's a good question. I'm not entirely sure about the answer, but it's RTGs. There are only so many. They do take a long time to produce, and they are expensive. So I think part of the reason for using the solar panels was that, they're more straightforward in terms of producing them. They're easier to procure, and we didn't necessarily need to or want to wait for as long as it would have taken to have gotten the RTGs we would have needed to power a Clipper. And there certainly would have been some advantages with those big solar arrays make it really inefficient to turn that spacecraft very, very quickly. So I know I believe that's one reason why we are flying with RTGs, or without RTGs, with solar panels instead.
Yeah, that's kind of my understanding as well. I think definitely the decision predates me on the project too, but there is only so much of that plutonium that is available to build an RTG, and it is not a trivial thing to get more. To make more is actually the correct way to say it, and that involves the Department of Defense and international conversations. So it is a complex thing to get RTG, and so. It's non-trivial, but Jupiter is about as far away as you can get and still use solar panels. I'm noticing my video is a little laggy. I'm gonna make sure. Yeah, okay. Might just be my internet having a little bit of a moment. When we're out at Jupiter, we get about 4% of the solar power that we would get at Earth. And so the sun will just kind of look like a bright star to Europa Clipper. And so it's kind of amazing to me to think about the fact that we have this these huge solar panels. We basically just have this bright star that is powering our spacecraft, but somehow we're still able to get enough power with that to be able to power this incredibly large and complex spacecraft. The person who asked the question about what the solar panels are made of, I'm actually not sure. It's a great question. I can tell you that they were made by Airbus in the Netherlands. We have very few kind of international partnerships or organizations that we've worked with on this project, but Airbus is who built our solar arrays. And so if you're curious, you can probably Google about it, and there might be Airbus might have published an article about, look, we just delivered these amazing solar panels, and here's all the technical specs. That's probably what I would do if I was interested in that. They're definitely kind of made for space and made for the really tough radiation environment that we're going to have at Jupiter. So they're complex and fascinating part of the spacecraft.
I believe
Yes.
it. Can we talk more about that radiation environment, but also like the arrival at Jupiter? Because I can't picture it right now, but the orbit that it's going to go into is orbiting Jupiter, right? Not Europa. And it's going to swing through that harsh radiation to kind of try and minimize or maximize its lifetime. So what are some of besides the chosen orbit, what are some other precautions or protective measures for the space?
Yeah, so as you said, Jupiter has this incredibly intense radiation environment, and that's because it has magnetic fields that are kind of trapping charged particles in the environment around Jupiter, and basically acting as like a massive particle accelerator. So it's kind of trapping these charged particles, and they're just whipping around and smashing into everything in their path. And Europa, the moon, happens to be in that path. And so Europa is just kind of bathing in this massive cloud of charged particles that are again kind of whipping around the planet. And so it's a spicy environment for spacecraft to live in. Charged particles and sensitive spacecraft electronics don't really play nicely together. And so we have a couple things that we do to mitigate that. As you mentioned, the orbit is probably the biggest thing. That radiation environment has driven the design of our mission. So we're not orbiting Europa directly. If we were, we might only last maybe a month or two before the radiation really started to damage our spacecraft to the point where it would be unusable. And so instead, what we do is we orbit Jupiter, and we kind of swing in, and we do these successive flybys of Europa. We have this kind of big elliptical orbit. And by swinging in, we can get a whole bunch of science data really quickly, and then get out of that radiation environment to downlink the data, do kind of engineering maintenance and things like that. The other thing that we've done is that on the spacecraft, the main part of the spacecraft body is a kind of a cube structure that we call the vault. The vault is literally just a box that has all of the really sensitive pieces of electronics in it. It's made of an aluminum zinc alloy material, and it's about 1/3 of an inch thick of shielding. And so that protects a lot of those most sensitive parts of the spacecraft from the radiation. So it obviously won't protect from everything, but it does quite a good job. But of course, not everything can be put into the vault, like the solar panels, for example, right? Don't fit in the vault. So we have that's why we can't just shove everything inside of a radiation protected little box and then orbit Europa and just survive in that radiation environment. We kind of have to balance the two.
Just like you can't build the whole plane out of the black box.
Exactly.
Yes.
Exactly. Yeah. Yeah.
What is the design lifetime? Is it 5 years or is it more of the Clipper mission?
Yeah, it's designed to last for 4.5 years. Whether or not it can go for longer, that's something that remains to be seen. I kind of suspect we can, but proof will be in the pudding.
Yeah, and that's 4.5 years once we get there, right? So we have a 5.5-year cruise, right? So which is again interesting from an engineering perspective. It's a totally different environment, right? We have to be able to also survive the inner solar system and getting out to Jupiter and the kind of different thermal environments and the different power configurations and such that it'll take to get out to Jupiter. And then we also have to survive at Jupiter for a number of years. So.
Yeah, and that was one of the benefits of using the Falcon Heavy is, earlier trajectories had us coming even closer to the sun. I'm coming to within point AU, so rough, sort of inward closer to Venus's distance from the sun, and that was going to be a very difficult designing for that, and then designing for the cold out of Jupiter, was going to be more challenging, and this allows us to sort of get away from that really, really, really hot part of the trajectory, the cruise trajectory that would have been.
Cool. And so speaking of the vault, there's also a really cool memorial sort of thing that's placed in it, this vault plate, that kind of represents humanity a little bit.
Yeah.
Can you talk a little bit about that? Have you both seen it in person?
I did. Yeah. I don't know, Sean, did you ever go see it?
No, I've not seen the vault plate in person.
Cool. Yeah. So there was kind of a very short window of time when it was visible in the from the like viewing gallery of our high bay, and then it was attached to the spacecraft and then boxed up and sent to Florida. So it was like a very short window where you could actually go see it with your own eyes. Yeah. So this is it's called the vault plate because it is basically what happened was the engineers kind of said, hey, there's a spot on the vault where we don't really have it's not already we don't need to put wiring there. We don't need to put anything else there. There's kind of just this open space. It's about the size of like a 8.5 by 11 sheet of like printer paper cut on the diagonal. So it's kind of this triangular shaped plate that was just available. And so there's kind of a long history of putting kind of artistic representations or kind of messages out to the stars onto our spacecraft, especially ones that go to the outer planets or beyond. And so an effort began to kind of create our own message out to the stars. And so this plate that you're seeing the photo of now, this is one side of it. And what that is each one of those little indications is the waveform for the word water spoken in about 104 languages. And that's because water is the thing that kind of connects our two worlds. It connects the Earth to Europa, and Europa to the Earth is the water. Underneath the ice on Europa is this massive ocean of water, and so water is the thing that really connects us as humans, to Europa. And then on the other side of the plate is everything on this side of the plate is something that was kind of written or drawn by hand. Again, kind of making a connection to the humanity and the people who've worked on this project. There's a lot on this side of the plate that's like maybe a little bit too much to talk in detail about, but the kind of most prominent thing that you can see is a poem. And so the lines of text that you can see there is a poem called In Praise of Mystery, a poem for Europa. This was written by Ada Limon, who is the US Poet Laureate. And she wrote this poem about Europa Clipper, and kind of about our connection with the earth and the water. It's an absolutely stunningly beautiful poem. There's a great video of her reading it with some animations that I highly recommend going and watching. And so she, after she wrote the poem, she wrote it out by hand in her own handwriting, and then we etched that onto this vault plate as well. This then kind of preceded a campaign that we did called the Message in a Bottle campaign, where we asked people to kind of sign their name to the poem, sign their name to the message that we were sending out to Europa. And about 2.6 million people signed up for that. And so at the very top of the plate, there is a literal bottle kind of shown within the orbit of the Galilean moons of Jupiter. And right in the center of that bottle, we mounted a very small little microchip that's about the size of a dime. And there were 2.6 million names actually etched onto that chip. So not encoded in ones and zeros, but actually with like an electron beam, actually written those names onto that chip. And then the chip was attached to the plate, and the plate installed on the spacecraft. So if you signed up for that Message in a Bottle campaign, your name is physically written onto our spacecraft that's on its way out to Europa. So that's the vault plate. It's a beautiful, gorgeous, amazing thing that was put together. There's more on that side of the plate that we could talk about, but it's a really incredible message.
But I also do want to point out that image, the man that was faced
The
on
portrait.
their side is Ron Greeley. Ron Greeley was a planetary scientist at the Arizona State University. He was the advisor to our project scientist, Bob Papalardo, and he was also involved in the Galileo mission and did a lot of work on Europa. He inspired a lot of the current scientists who are working on the mission today, and I think it's sort of a shame that he's not alive with us to see this happen. But you know, it was definitely sort of one of those figures that you want to remember. And so in some ways he is going.
Yeah, exactly.
Good for you
Yeah,
guys.
it's amazing that we're able to honor him in that way.
Hagen,
It's almost it's almost
questions from chat.
Yes, I do. So our radiation discussion a bit got quite a few questions coming in from chat. And so the first one is, regarding the mission at the end of its primary mission, we hear often of missions that, are in fantastic health when they reach the end of their primary missions, and then ultimately teams will, sometimes submit mission extension proposals. And so whenever Clipper reaches the end of its primary mission, assuming your team, doesn't go forward with a mission extension, how have the conversation started on how we're going to be disposing, of the of Clipper? Are we going to leave it in orbit around Jupiter, or are we going to, do maybe sort of a Cassini and, either send it into Jupiter or to Europa? So, had those conversations started?
Definitely. Sean, do you want to take a crack at it?
Oh, yes. Yeah, they definitely have. It's sort of an essential part. NASA has planetary protection rules in place. So we really do have to think about this before we even launch. And the current plan actually is to crash it into Jupiter's moon, Ganymede. And the interesting part about that is that the European Space Agency has a mission called JUICE that is also en route to Jupiter. And at about the time that would happen, that spacecraft will be circling around Ganymede. So they would get a fantastic view of that impact, and that would give them a chance to sort of study whatever gets kicked up in the impact. But I'm keeping my fingers crossed that we go for a little bit longer than that.
Yeah, exactly. And it was a really interesting conversation, the kind of which moon of Jupiter do we crash into? Why not Jupiter itself? And the kind of, there was a trade done basically. So Jupiter, of course, as Sean said, we don't want to crash into Europa because Europa is a potentially habitable world. And just in case we brought any little microbes with us, even though, we do clean our spacecraft and try to keep it really clean because we're going to a place that could support life, we don't want to accidentally crash into Europa. So at the end of when Europa Clipper has kind of fully lived its life and it's, we're kind of at the end of mission, we don't want to just kind of leave it in an orbit and let it just orbit there on its own forever, because at some point it could hit Europa and we don't want to do that. So we want to make sure that we dispose of it safely. Of course, the spacecraft would get vaporized if we crashed it into Jupiter, which, from a kind of cleanliness perspective, is maybe the cleanest option. But it actually takes a lot of fuel to change the orbit enough to hit Jupiter, and we would rather use the limited resource of fuel that we have to do more science orbits, right? To change our trajectory to view different things on Europa. And so instead, it was determined that it would be kind of safe as Sean was saying, from a planetary protection standpoint, to crash into either Ganymede or Callisto, which are two of the other Galilean moons of Jupiter. And they're a little bit easier to hit from a engineering perspective and from a fuel use perspective. And so it was a kind of it was probably the most fun meeting I've ever been in, is the meeting where we talked about kind of like which moon of Jupiter should we hit with our spacecraft and why. And of course, the fact that JUICE is going to be there and could potentially observe our impact. There's a lot of science you can do from what it then essentially becomes an impactor mission, and kind of understanding, the things that get kicked up and what the kind of the crash site looks like will tell you a lot about the behavior of the surface and things like that. So it was a really kind of again, a bit of a surreal conversation of like, okay, so we're picking a moon of Jupiter to crash our spacecraft into. That's very cool. I never thought I'd get to be part of that conversation.
Yeah, and you mentioned JUICE there, the European Space Agency's Jupiter Icy Moons Explorer mission, which launched last year and is also currently en route to Jupiter. A question from chat here is asking about the two missions. How are they different, other than the fact that JUICE is going to be focusing more broadly on all three of Jupiter's icy moons, which are Europa, Ganymede, and Callisto? But how are the two spacecraft, Clipper and Juice, how are they different, but also how are they the same? How are they going to work together, so to say, whenever they're in their orbits around Jupiter?
Yeah, Sean might know more about this than me, so I'll share what I know, and then he might jump in here. But yeah, they're in some ways very similar spacecraft. Obviously, they're going to a very similar environment. So from an engineering perspective, they have to be kind of designed in a lot of the same way. You can see, they also have these big solar panels and this kind of central body, and it kind of on the broad strokes, they look very similar. There are some at least one that I can think of off the top of my head there that where there's an instrument that is kind of the same on both spacecraft, and that is that Europa Clipper has an instrument called Reason that we were talking about earlier, and JUICE has an instrument called RIME. Yes, RIME and Reason, and they are both kind of radar instruments that are doing very similar science on both of the spacecraft. Sean, are there other kind of like similarities or differences with JUICE that you're more familiar with?
Yeah, well, I mean, coming from the ultraviolet spectrograph perspective, UVS, my team back at San Antonio, our team who built the ultraviolet spectrograph, also built one for JUICE. So there is a JUICE UVS, there's a Europa UVS, and those two instruments are almost exactly identical. RIME and Reason were built by two different institutions, but they are meant to function in very much the same way. So I actually am hard pressed to think of fundamental differences between the two spacecraft. They are much more alike than they are different. The instrumentation is a little bit different. The JUICE has an antenna to measure plasma fields. It has a Langmuir probe that we don't have. So there are a few different differences in the instrumentation on the two different spacecraft, but most of them have, they have a camera, we have a camera, we have a near-infrared spectrometer, they have a near-infrared spectrometer. So there are many more similarities than differences between the two. And that actually is sort of going to make this into a very exciting opportunity. You have two different platforms that will be in the Jupiter system at the same time and be able to take similar measurements from different vantage points. And there's going to be a lot of exciting science we can get out of that.
Yeah, that's awesome. It's so cool that JUICE is going to be there at the same time, and and studying different moons. But there are some things that Europa Clipper will do that JUICE will also do, right? Like JUICE is focusing on some of the other icy moons, not focusing on Europa, but there are places where we're going to be studying the same thing, and and of course studying the environment in general, understanding the magnetic fields, the plasma fields, the radiation environment, the gravity environment, where both spacecraft are going to be studying those things that kind of affect the entire Jupiter system.
Yeah, and there's one orbit in particular where we are going to fly by, I think we're going to fly by Europa within, I think, 4 hours of JUICE. So that'll be some really great comparative science.
Yeah.
We've not done anything like this in the outer planets before, so.
Ever. Yeah. It's awesome.
Yeah. And then you mentioned there those other moons. So obviously JUICE is going to be looking at those other moons, but a good question from chat here is asking, obviously the focus of Clipper's mission is on Europa. However, will Clipper look a little bit more into Ganymede and Callisto? And if it does, what would those types of observations look like? Would they be more direct observations where the spacecraft like literally looks at Ganymede and Callisto, or will it be sort of observations built off of the observations Clipper makes at Europa?
Yeah, it's a great question. So there's a couple ways to kind of tackle it. So one is that we are definitely going to be flying past Ganymede and Callisto on multiple occasions, and we actually use those moons to change our trajectory. So we sometimes it's easier to fly past a moon to change the trajectory of Europa Clipper rather than just relying solely on thrusters. And so we when we first arrive at the Jupiter system, we will actually, I can't remember if we do both Ganymede and Callisto in the very early part of the mission, but we definitely do one or the other as kind of our first flyby is one of the other moons to help change our orbit and actually get us into the correct orbit. And so we do some Ganymede and Callisto flybys then. And then we also have there's kind of two halves of our mission. We have kind of two major Europa campaigns, what we call them. And in between those two Europa campaigns, there will also be a bunch of Ganymede and Callisto flybys again to help change our trajectory and get us into the right orbit. As far as the science that we might do at those moons, I will give the kind of right answer, which is that we are definitely a Europa mission, and so in a arena where things are constantly constrained, where we have very limited fuel resources, we have to be, cognizant of how much data we're bringing back and things like that. Europa science will always kind of take the first place spot, right? And so that doesn't mean that we may not do some science at Ganymede and Callisto, but the Europa science is definitely the thing that will kind of always win out the day, because that is the kind of prime goal of our mission. Yeah, anything I missed there, Sean, or you want to add about Ganymede, Callisto?
Yeah, I mean, I will add that. So initially, those first few, what we call the pump down orbits, are going to be just going past Ganymede. I will admit, I
Did you
didn't know
check real quick?
off my head, but I checked.
Okay, cool.
And then there's going to come a point where we change the character of the orbits. So there's going to be a brief sort of intermission between the first set of flybys of Europa and the second set of flybys of Europa. And during that sort of intermission, for want of a better word, we will have more Ganymede and Callisto flybys and more opportunities to calibrate the instrumentation. And if some science falls out of that, so be it.
Right. It's not like we're going to like turn off the spacecraft when we fly past Ganymede and Callisto, right? Like we will have things there. It's just in a arena where things are constantly constrained. If it makes more sense to, say, actually we don't want to spend the resources to do a certain thing because we want to make sure we're saving enough for the Europa flybys that are coming, like that may end up, kind of winning out the day, right? But it just depends. It's really it's tough to say until we get there. Exactly how that trade will fall out. So
does nobody have enough for IO anymore?
I know.
we do love IO. So we don't ever use IO to change our orbit, and I don't quite know the reason why. I would guess it's because it is really close to Jupiter, and it just doesn't quite give the same advantage in changing our orbit. Although IO has a really interesting contribution to the kind of science, like in general, right, Sean, because of the plasma torus and all of IO like spewing stuff out into the environment all the time.
Yeah, that's part of the reason why the radiation environment is so intense. I mean, it's the radiation environment. There was a graphic that we were showing with the elliptical orbit of the spacecraft, and it sort of depicts how the radiation environment is intense, sort of in the Europa IO sort of range of distances from Jupiter, and that's because volcanic IO is constantly spewing out gases and particles into the magnetosphere, and these atoms very quickly get charged through interactions with Jupiter's magnetosphere, and so they form this huge this IO torus. It's just spewing out sulfur dioxide into the system, and these are some of these charged particles are what we're talking about in terms of this radiation. And I have this idea that we will be able to do some interesting occultation experiments with any of these moons. I think that you don't necessarily have to fly right past Io to observe an occultation. Sort of when the moon itself blocks a star from behind, you can look at the star and sort of measure the environment right around that moon. And that might be something that we could do. It's something that, JUICE definitely would have in its purview to do when it gets there.
The way you describe the environment around Io makes me think that Io just wants to be left alone.
I have so every time we talk about Io, I just feel like I have to mention this, that okay, so Jupiter is incredibly massive, right? It's this massive planet. It's just so big, huge gravity. Io is the closest moon that is orbiting Jupiter, and it orbits Jupiter, I think, every 18 hours. So think about that for a second. right? Maybe it's 17 and a half or something, but it's around 18 hours is its orbit of Jupiter, and it's just whipping around Jupiter. Like that's so fast. And Europa orbits every 3.5 days, which is also really, really fast. I mean, our moon orbits the Earth every, about 27 days, right? About a month. So just thinking about that Jupiter is so big, and you've got these moons that are about the size of the Earth's moon, or maybe a little smaller, just whipping around Jupiter. It just kind of blows my mind.
Yeah, it's really cool. You can see through a telescope, and you can look like just like an hour or two later, and Io's moved, and maybe some of the others have kind of moved.
Right, visibly. Yeah, I really want someone to make an animation of like, what would it if I could stand on the surface of Jupiter, if it had a surface that it could stand on and was looking at Io in the sky, like could how much would it move? And anyway, I want someone to make that animation, so I'll just put that out into the universe and maybe it'll appear.
But also what's mind-boggling is Jupiter orbits once every 10 hours. Sorry, spins on its orbit. So, I mean, it's
a wild place. It really is all of that kind of stuff put together, right? It just is you can see why it's a fascinating place that we want to go and learn more about.
Yeah. Sean, I wanted to ask you some more about science. So you were talking about UV spectroscopy earlier. So what kind of stuff will that help us learn about Europa's surface? And if we throw up some Europa surface images, can you tell us anything about the features, or am I asking the wrong person?
I can at least make a nice educated guess about some of these things.
So Evan, if you could bring up any of the surface images that'll have some features on them.
Yeah, so I think maybe this is the do we know what the title of this one is?
This is Juno's view.
This looks like the Juno image.
That's what I thought.
It's a natural color. Yeah.
I was going to guess. So one of the things that you have to note, or that jumps out at least at me immediately, one is how very, very bright the surface of this moon is. You don't see very many impact craters. Like there might be one right there. It's very featureless. It's very smooth. This automatically tells you that something really interesting is going on in this world. I mean, there's a lot of reason why we have a specific interest in Europa. So what these images immediately tell you is that it's obviously got a very youthful surface. Any surface like this that sits out there in space is going to be exposed to impact from comets, from asteroids. And if you look at the other moons exterior to Europa, you quickly see all the impact craters, and Europa is somehow, like the Earth, very effectively erasing these features. And so we now understand it's because we have this youthful icy shell that overlays this ocean. Yeah, I forgot where else I was going to go with that. These cracks that crisscross the surface are another sign that it's got geologic activity that's ongoing. And so the very fact that there's so much activity makes it just that much more intriguing of a place to go.
Is so our UVS experiments going to be helping us understand kind of like what things are made of, right? I mean, because it's a spectroscopy experiment, right?
So one of the things that the ultraviolet spectrograph will be very, very well poised to do is to help characterize any potential water vapor plumes. We know that at Saturn's moon Enceladus, we've seen this, you've probably seen images of these water vapor plumes that are coming out of the South Pole. We have some indirect evidence that this could be happening at Europa. And if this is happening at Europa, it's a great way to sort of explore the nature of the materials that are right beneath that surface. The ultraviolet spectrograph will be particularly useful for looking at these occultations. I've referenced that before. So remember, the sky is full of stars, and if there are any plumes and they should happen, a bright star should happen to pass behind that plume, the ultraviolet spectrograph would be really good for characterizing how much stuff is there by looking at the starlight and the way it dims. You look at the colors, and the way the colors dim will help you tell what exactly is in that. We expect that it'll be mostly water vapor, and the ultraviolet is a really good place for detecting water vapor and characterizing it.
Very cool. I want to remind everyone too that I forgot, it's roughly, we think Europa roughly has like 3 times the amount of water on Earth, correct? But it's only closer in size to our moon.
Yeah, it's about twice as much water is kind of our best estimate right now. And but yeah, it's about the size of our moon. So again, just think about that for a second, right? Like the Earth is, I mean, we have a ton of water here, right? We have all these oceans and clouds and rivers, right? I mean, there's just so much water on the Earth. Take all of that water, double it. That's what's on Europa, which is about the size of the Earth's moon, a little bit smaller, just underneath the ice, right? And so it's incredible to think. And every time I think about it, I kind of like get a little like stop in my tracks, because it's just the fact that there's another body in our solar system that we can get to in a reasonable amount of time with that much water. And at least on this planet, wherever we find water, we find life. How could you not want to go there and see what's going on?
Yeah, I think about it in terms of the fact that we tend to think of the Earth as the water planet, but really
Right.
the solar system, we know that, whether it be in the form of water or water ice, there's really a lot of this in the outer solar system.
Yeah.
And you mentioned, or we were talking earlier about how small, the sun is from Jupiter. So it's clearly not liquid water because it's closer to the sun. But it's more, we think, sort of this tidal friction, right? The pull of Jupiter that kind of elongates and moves the crust on Europa, that is enough to potentially keep some amount of that water liquid.
Yes, and so there's an interior image that we have somewhere sitting that we could probably
Cross section.
the cross section, yes. Yeah. And so that's the one, right? And so we know that there's this ice crust, right? And we know that there's the liquid ocean beneath it. And you're right, it's not kept liquid because of any interaction with the sun. There simply isn't enough energy coming from the sun to melt ice that's that cold. But there is tidal energy that is being dissipated in Europa. And so much the same way that Io has all these volcanoes because of its tidal interaction with Jupiter, we believe that there is some level of tidal dissipation going on at Europa. And that is the energy that keeps the water ice or the water liquid.
Yeah, exactly. And it's, the kind of easy way to think of this is that when we kind of simplify models of things, we tend to make moons perfectly spherical, and we tend to make their orbits perfectly round, and we center them perfectly on the planet, right? To kind of like simplify things. But in reality, Europa is not a perfect sphere. It is definitely a little bit misshapen. Its orbit does not sit kind of perfectly with Jupiter in the center. It's a little bit off center, and its orbit is a slightly elliptical. And so all of those kind of things combined cause the moon, as it's orbiting Jupiter, to kind of stretch and squish. And it's kind of just like I use the example a lot of like playing with a rubber band, right? That if you're playing with a rubber band and you're just like stretching it and relaxing it and stretching it, relaxing it, it starts to warm up, right? It gets warm from the kind of that motion gives off heat. And so kind of the same thing is happening at Europa, but just on the scale of a moon. And so that and then we know too that if there was no kind of material in the center that could stay warm, that we may not have liquid water, right? But we know about we know that this kind of layer structure of ice, water, rocky mantle, and then a metal core. We know about that from kind of previous measurements that we got from the Galileo spacecraft that helped us infer those different layers of Europa. And so knowing that it has a very similar structure to the Earth, actually, I mean, if you imagine you're at the center of the Earth and you come up to the surface at the North Pole, right? You're going to have this kind of warm center and then go through a rocky layer and then go through some water and then go through the ice. That's a very similar structure to what we have at Europa. And so, yeah, that kind of tidal flexing and that heating that happens keeps that water liquid.
So I just want to make Yeah, and I just want to make one more point about that, Jenny. That's a
Yeah.
really good point to raise. The fact that it undergoes that tidal stretching is related to the fact that it has an eccentric orbit as it goes around Jupiter. That is, it's not perfectly circular. It's a little bit like an oval. But eventually, what would happen if that were just simply the case, that Europa had this eccentric orbit? Eventually, that orbit would circularize, and it would no longer experience that tidal yanking and pushing and deformation. It's a system, and a very key point here is that Io and Europa and Ganymede are doing this complex orbital dance whereby Io orbits twice for every time that Europa orbits, and Europa orbits twice every time that Ganymede orbits. And they tend to reinforce this. They're in resonance. They reinforce this fact that they're all in these eccentric orbits, and they stay in eccentric orbits. So we know that the fact that the water on Europa's liquid is something that has been going on for a while, for as long as Io and Europa and Ganymede have been doing this dance.
Yeah, that's a great point.
Cool. And one of the coolest things about Europa to me, besides the fact that it has a literal ocean, is its surface. I have always found Europa's surface to be really interesting, and to the point that that Sean made earlier, there's no really evident craters and such like that on Europa's surface, but rather there's these long, expansive ridges. Yes, this is a fantastic image. So I feel like a lot of people are sort of like, okay, why no craters? Why these ridges? So I was wondering if you guys could, go into a little bit about, what are these ridges? What do we think they are, at least? Why a lack of craters? Like, why doesn't the surface of Europa look like that of the moon, like our moon?
Yeah.
And yeah, how will Clipper look into this? Will Clipper look into this? And if it does, what are you guys going to really look into?
Yeah, so I'll just say that the kind of 10,000-foot view that Sean mentioned a little bit earlier is that it's not that Europa was hit less, right? It doesn't have fewer craters because it was bombarded less than other bodies in the formation of the solar system. It tells us that there's something going on that is keeping the surface kind of young, at least in a geologic sense, that over time something has been refreshing the surface. It has been changing since it was hit. So Europa was hit kind of with, bombarded with things just as much as the Earth's moon. But the fact that there are so few craters now, and there are some, but they're just very few, tells us that something is going on that kept that surface young.
It's constantly recycling the surface. And so we don't fully understand the kind of technonism that happens at Europa. And that's one of the things that we want to understand. We want to understand exactly how these ridges form. We have some idea from Galileo. And I remember, speaking of just how fascinating the surface is, one of the more exciting things to me when I was a graduate student was working with some of this Galileo data. And I remember it coming down, and my fellow grad students and I, we would just look at the new images and just sit there and stare at them and like, wow, how do you think that got here? What happened like that? There's like this image right here, I think is just absolutely fascinating. This one little flat spot in the middle of all this mess. And it's got obviously this very complicated system of grooves and ridges. And if you look, you can see places where there was a crack or a ridge, and then somehow it got offset from one another, from itself on the surface. So it's a pretty complicated system of technonism that's happening there. And we'd like to study that more, get more images, more data, do a more complete sampling of the surface itself. This image is of what we call chaos terrain, where it looks like there was, and you can sort of see these offset ridges in this image, and it looks like there was, a pre-existing surface with these cross-cutting ridges that somehow got disrupted, and somehow they broke up and floated around relative to one another and then got frozen again in place. It's like someone smashed the surface and created this jigsaw puzzle, and in between you have this, what we call this matrix. Exactly how this happened, we don't know, but obviously it involves the heat and sort of melting of the immediate subsurface, and there's a lot here to learn.
Yeah, and we do actually see some of these kinds of, especially the you'll notice that with these ridges, they're in pairs, right? There's always this kind of double ridge, and we see that structure. And again, this is not my area of expertise, but I know that I've seen some papers that like we see this structure in Antarctica on the Earth, and so there's a lot of interesting things that we can actually study on the Earth that might tell us what is going on at Europa as well. And I know that kind of one of the most interesting things that we want to understand on this mission is that ice-ocean interface. Where the water is touching the ice, that makes the ice a little bit warmer and the water a little bit colder, and so you get kind of convective effects where there's kind of exchange, and maybe things are a little slushy. And if that's in a spot where the ice is thinner, that could cause the surface to break open or rupture or flip apart, right? So that kind of understanding what's going on right where the water meets the ice is really, really fascinating. That's one of the things that our reason instrument is going to help us understand. And yeah, it's just really, it's a really incredible thing.
Themis will lend to this understanding as well. The thermal imager will look for places that are warmer, and it's still going to be pretty cold, but relative to the melting point of water, you will be able to detect these slight differences in heat.
Yep.
And reason will also look for little subsurface pockets of water. There are places where it looks like there was like local melting, and you would use these instruments to be able to tell you something about that. It's really a payload where the instruments have been designed to work synergistically together. Yeah, this we call this the mitten. I remember seeing this one for the first time and just being dumbfounded at
what is that?
What could have created that? How did that happen?
Right.
And it's just one of the most
cool.
fascinating things about doing planetary science is getting this new data and just seeing things that you just simply can't quite understand at first.
Yeah. And so that takes me to something. This is a question I always love to ask scientists that I interview. And that is, and especially whenever, I'm interviewing somebody that's worked on a mission that's now on its way. And that is, there's obviously a lot of unknowns with Europa. And that's why we're going there. That's the whole reason why we're sending a mission there right now, is to learn more about this amazing moon. And so I want to ask you guys, is there specific things regarding Europa that you guys are really, really, really interested in, and that you don't really have much knowledge on because we just haven't been there yet, that you're really looking forward to finding out whenever Clipper gets there?
Sean, do you want to take that one first?
Well, I think this is a pretty good image. This is what we call macula. One is called Thera, one is called Thrace. We're going to fly over both of these and sort of getting at the nature of this. We know it's mostly water ice. We can tell that. We've known that for a long time. You can tell that from the Earth. But it's the other stuff that's there, right? The slight discoloration is telling us that there are non-water ice species on the surface, and sort of learning more about the nature of that. Some of it is we're going to find out that it's sulfur and sulfur derived products that are coming off of Io, but we believe that there's more stuff there. And really, these would be the things that life would have to work with down in the ocean. So part of this whole story is that because the surface is youthful, we believe it's being constantly recycled. Stuff that lands on the surface likely somehow winds up down into that ocean through this recycling of the crust. And that will give us some insight as to what anything that is in the ocean might possibly have to work with as building blocks for life. And I think sort of uncovering the nature of that will be pretty key, a very big part of the mission. And just understanding how all this stuff works, all these little pits and domes that you see.
Yeah, that's super cool. And it's it's funny because like as an engineer, my excitement about Europa is kind of I guess like a little more broad, right? I tend to get excited about the fact that there are places on the surface that we don't have pictures of, or that we do have pictures, but they're really low resolution. And so, if you look, there's I've seen this comparison of an image from Galileo, and then I believe from Juno when we did that one flyby in 2022. There's kind of one spot on the surface where we have, the same spot on the surface from the Galileo spacecraft and from the Juno spacecraft, and you can see the difference in resolution just from those two cameras, and it's mind-boggling. The image from Galileo, it's like, oh, okay, there's this kind of dark region, and then when you see it from Juno, it's like, oh my gosh, it's actually like 5 different regions. They're all like, this thing that looked like a homogeneous part of the surface is actually like really, really different just because you have a much higher resolution image. And so to know that we're going to do that again, that we're going to then have another kind of, big step change of understanding of kind of getting the imagery of Europa, and knowing that even things that right now look like, wow, you can see such amazing detail in some of these photos, but to know that it's going to get even more, and just kind of, the other thing I think about is that, we discovered the ocean under Europa basically by studying the magnetic field data from the Galileo spacecraft, which when as someone with an engineering background, when I first learned that story that, by studying the magnetic fields, and we could see that there was some kind of weird interaction happening at Europa that was a little bit unexpected. And that kind of led us down this path of going, oh, there must be a conductive layer that's conducting the magnetic fields through this body. And the fact that we learned that from magnetic field data, right? We discovered that there's an ocean not by taking a photo of it and seeing, oh, there's water there, but by studying magnetic fields, we were able to make this incredible inference about what's going on inside the moon. Thinking about that kind of scientific reasoning and knowing that there are going to be other things like that, where, by studying this one thing, we might learn something about Europa that we didn't fully expect. Just that's super exciting to me. It's like fundamental science.
Yeah, there's that image there. Thank you, Kevin, for putting this up. It says here that taken by one of these images is taken by Juno, and then on the right is an image from Galileo. So, like you can see, like Jenny said, you can see those differences there.
Right.
It's really
Yeah.
awesome. And that's another. Go ahead. Sorry.
I was going to say, and the fundamental thing is just that it's not that we have better images or closer images. I mean, that's great, but it really provides you with a fundamentally different understanding of what's happening on the surface. Like, you have this sort of fuzzy image and you think you know what's going on, and then suddenly you get a more clear view and you realize, oh, wait, things are happening here that we didn't understand before. So it changes your understanding of what's happening.
Exactly. Yeah, it's really cool.
Yeah, and we're starting to run out of time here, but I did have another question. So we talked about Juice and Clipper earlier. However, Juno is already in or orbit around Jupiter. So I was wondering if you guys ever work with Juno's team to sort of, and will you work with Juno's team throughout your coast phase to sort of prepare your teams and Clipper for what to expect at Europa? Is Juno taking data at Europa? Obviously, we have its flyby from a few years ago. During that flyby, for example, did you guys get any input and ask for maybe some specific observations that could help form your understanding of Europa and what you're going to be doing whenever you get there?
Yeah, it's a great question. I mean, so Juno is in a very different orbit, so it doesn't quite have the same ability to just real quick do a flyby of a moon in the same way that that Europa Clipper will, and that's just based on the orbit that it's in. But occasionally, it does kind of have the physics works out that the bodies are in the right location to be able to do a flyby. So Juno is kind of studying Jupiter, and the Jupiter environment as a whole. It's not meant to its prime mission is not to study the moons. And so, we have gotten some flybys. I think there were actually 2 kind of, several months apart from the Juno spacecraft, and one was a little bit closer and one was further away. And, I don't think we were able to kind of request a particular observation because it was just well, the spacecraft will be able to get what it gets from this flyby, and we will just absolutely love whatever data we're able to get back from that. But again, from kind of on the hardware side of things, we definitely learned a lot from the Juno spacecraft about the radiation environment and how that spacecraft is performing under that intense radiation, right? So that will tell us a lot about how Europa Clipper might perform as well.
Yeah, the Juno spacecraft is essentially in a polar orbit, and as Jenny said, it's really intended to study the planet itself. And as that orbit has evolved, it's afforded the Juno mission views of, first Galileo, Ganymede, and then Europa. It's recently got some amazing images of Io, and that orbit's going to continue to evolve as they go into their extended mission. And just like there is a UVS on JUICE, there's also a UVS that was built by the same group in San Antonio that's on Juno. It's also a spinning mission, so it's not really designed to get these images, and the fact that it's doing as well as it has with some of these things is pretty incredible. So yeah, I mean they're operating as their own mission. They take the data that they feel like they need to take, but they definitely made some amazing contributions and help put some of what we're going to see into context.
I love that there's this team that just churns out these UV instruments for all the
Yeah, it's a very bespoke UV spectrograph factory.
They're done.
So as we sort of chatted about when we did our tech check last week, the time runs out before you even know it. And
Yeah.
we could continue going on for hours, but we will not keep you that long. I did want to kind of ask a little bit of a wrap-up question, which I think we've kind of touched upon in the conversation just now about what you're hoping to see or what you were hoping to be surprised by. But if there's one thing that people take away from watching this stream today about this mission, what would you like it to be?
I think for me, I mean, the thing I always think about with, and the reason I got excited about Europa Clipper and Europa, in years past, like before I even worked on this mission, is the fact that this is a potentially habitable world in our solar system that could have life on it today. Right. So we've studied Mars a lot. We know that Mars, may have had past conditions for life, but we're not, fully certain of that yet. We know that there's some ice at the poles at Mars. We know that there's probably some ice in the shadowed regions of the craters on the moon at the poles. And of course, we know the Earth is abundant with life and abundant with water. But the fact that there's another place in our solar system that we can get to kind of in our lifetimes, right? Within a few years, we can get there and is abundant with water. We think it has the chemistry. We think it has the right energy source. Of course, it has the water. And we think that Europa has kind of been simmering away under these conditions for about 4 billion years. So it really is kind of our leading kind of candidate in the solar system to look for a habitable environment outside of the Earth that could be habitable today, right? This isn't something that we're looking for, like, was it habitable in the past? This is right now. And to know that, that the possibility, of course, in my wildest imagination, if life exists there in any form, right? The fact that there is life in two places in one kind of ordinary solar system, of course, opens up the question of, like, how common is it in the universe? What would that mean for the kind of distribution of life in the universe and in our own galaxy? I don't know. When I start to think about that, it just blows my mind that, like, if we, the discoveries that we might find at Europa and how that could impact our understanding of our place in the universe, it's just mind blowing.
Agreed.
Yeah.
Yeah, I mean, I would add, even if none of this were true, the things we've talked about makes it clear, or I hope makes it clear that, this is a really exciting place in the solar system to go explore. And the fact that this is probably our best bet for a currently an inhabitable ecosystem is really fascinating. But I also think that we should look at this as a first step. I think that we're going to go do some recon here. We're going to explore Europa. And I think that really opens up the possibility for future missions to really look at this world in more depth, should we decide that that's warranted.
I think if, Cassini and Juno and even the Mars rovers are anything to go by, this is going to ask more questions than it's going to answer. And
Yes.
I'm looking forward to all the, like, what the what moments, start getting the data and the images. So I think it's really, really, really cool. And I'm so glad we figured out about it today.
It will revolutionize our understanding of the system. I mean, that I can conclude. I think we know that.
And hopefully in the future we can like actually send a landed mission to Europa too, right? I mean, that's the obvious next step is, okay, let's land on the surface for a little while and see if we can melt through some of the ice and take some samples directly, right? Of course, we all want something like that at some point.
I have worked on a mission. I have worked on a mission concept that would do exactly that.
Exactly. Yeah.
Yes, I wish we had time to talk about it. Like Summer said earlier, we could sit here and talk for hours, but we won't keep you for too terribly long. But yeah, I think that's going to wrap it up for us here today on the Astro Virtual Live. So thank you so much to everybody that's watching. Thank you so much to Jenny and Sean for giving us some of your time from your weekend. I know you guys are very tired after a very busy last few weeks. So thank you so much for sitting down and talking to us about this incredible mission. I know I can speak for a whole lot of people whenever I say that we cannot wait to see what this mission is going to do in a few years. But yeah, so thank you so much to everybody that's watched. As I said at the beginning of this broadcast, Astro Live is supported through a NASA cooperative agreement awarded to the New York Space Grant Consortium. And for next month's Astro Live, I will not be here. Doss and Alicia will be back, hopefully. And coming up next month, we're going to be leaning into all things food and Thanksgiving by featuring food and space. Our special guest will be a former manager of NASA Food Systems for the Space Shuttle program in the ISS, who is also an author and who will talk with us about developing meals for long duration space travel and the future of food and space. So, and you can learn more at intrepidmuseum.org. But yeah, thank you so much to everybody for watching. Again, thank you to Jenny and Sean, and thank you to Summer for being my co-moderator and getting us through today and asking some awesome questions. So yeah, thank you guys so much, and we will see you next time. Bye.
Thank you for
It's a
giving us the
pleasure.
opportunity to talk about it.
Yeah. Thanks, guys. It was really fun.
Awesome.
And here we go. We have liftoff.
Propulsion continues to be nominal.
Our CPA chamber pressure looks good.
Rolling up. Roger, roll, Atlantic.
Water towers fly! Yes! Tango down to nominal.
Flighting outside of lead off. Bring in SPD off. It's orange!
Oh my God! Oh my God!
Decollage. Put that in the big bag, Eagle.
343 unfolds to go.
Indeed.
We rise together back to the moon and beyond.
This methane will be igniting in the flare, correct?
Yikes. You good? Sure. We don't need any more of these.